Hey everyone, we're going to prove this equality right here that says that the union of events EI then intersect with F is the same thing as when you intersect the events EI with F first and then take the union. So to prove this, we're going to use a technique that we show that one set is a subset of the other, and then show that the other set is a subset of the previous set. When two sets are subsets of each other, this will imply that the sets are equal. So that's going to be the main idea of this proof. So to start off, we're going to show that the first left-hand side of the equality is a subset of the right-hand side. So I is going to be an element of the natural numbers. The reason we're doing that is because we want to be a little more precise on the notation. I is an index right now. So this is our goal. So first, we're going to show this right here. So right now I'm just going to go back and finish our goal before I continue. Okay, so we're starting off with the left part first. So by doing this, or to show this, we're going to assume that we have some element belonging on the left-hand side set, which is this set right here. So what's going to happen if we do have a member of the set? We want to show some properties. By doing that, we're going to show that X is an element of U subscript I, where I is an element of the natural numbers of EI, and X is an element of F. So why is this true? This is true because of the definition of an intersection. E subscript I, when it's placed right next to F, stands for the intersection. If X is an element of the intersection of two events, then it is by definition an element of both events. So that's why we have this. So this here then implies that X is an element of EK, where K, or for some K element of the natural numbers. So it's just saying that X is an element of one of the sets in the union of this set above. And this is by definition of X being an element of a union. So by knowing that X is an element of some event in the union, we'll call it K. And it's also an element of F. We now have that X is an element of EK, F. So it's an element of the intersection of event EK and F by definition. So we know that I runs over the natural numbers. And we also know that EK, F is included in the union because EKF is included in the subscript I, because I is a natural number and K is a natural number. Then we can say that X is an element of the union of the intersection of EIs and F. So this last line here then shows is a subset of the unions of the intersection of events. So that's going to be the first half of the proof. The second half is going to be the same thing, but we're trying to show that the right-hand side is a subset of the left-hand side. And it's going to be a very similar idea. So we want to show and we're going to start off exactly the same. We're going to assume that this right-hand set of events is non-empty and that X is a member of that event. If X is a member of that set, then X is a member of EK, F for some K element of the natural numbers. So this follows by a definition of X being a member of a union. If X is a member of a union, then it is a member of at least one of the events. It can be a member of multiple events, but is at least a member of one of them. And we're going to pick EK to be that specific set. Because K is a member of EK intersection with F, then by definition of an intersection, X is an element of EK. and X is a member of F. And after this line, we have shown that X is an element of the union of events E. So the reason for this is because K is included in the union. So therefore it is a member of the union. We know that X is also a member of F. Then by definition of an intersection, X is a member of the intersection of this set of events So we have shown what we wanted to show. So we have shown that either way, or whichever way you pick X to be a member of which set, both sets are subsets of each other. When two sets are subsets of each other, then they are implied to be equal, proving the desired property. Okay, so now we're going to prove a very similar property. It's going to be slightly different. So what we want to prove now is so we want to prove that when you take the union of events E and then the intersection of F, it's the same thing as first taking the intersection of all EIs with F and then taking the union. So to prove this, you could also use the same technique as we did before, where you show that both sets are subsets of each other. But this time we're going to prove it a little more direct by using properties of the union and intersection. So we're going to first assume that all properties for finite sets, specifically the distributive property, applies to infinite unions. So let's start with the left set of events. So let's expand this out. So meaning we're going to take the first event E with the union of the second event E with the union of the third event E, and so on. But then intersected with F. So now we're going to use a property that when you want to take an intersection F and distribute it inside the parentheses, you're allowed to, as long as you do it to all the sets inside the parentheses. Just being careful of how you place the new parentheses. And so on. So these intersections EIF, E2F, E3F are now new single events. So now, because each event is taken with the union of the next event, we can write that all in one compact way by saying that the union is being taken of the intersections. But right now, we actually don't need those parentheses. So you can take them out if you want to. So this proves the second desired property.